Hey, this is Math 8, Unit 1, Lesson 10, Composing Figures today. And so today we looked at some variety of triangles and you were using some rigid transformations to discover some interesting information about measurements, whether that be line segments or angle measurements as well. And you began first of all looking at an isosceles triangle. We will call this one ABC right here. And as isosceles, we call it that because it has two sides that are the same length. 3 and 3 right there. And what we're doing is we're reflecting this triangle over line AB. So this is AB. That reflection point would cause this triangle to kind of fold over this way, and we can kind of think of it this way, reflecting it over, and would give us a triangle looking something like that. And so if I made my new point on that mark, I would put it somewhere about here, it looks like, somewhere about here. And we're making a copy of that triangle like so, and it said to call that new triangle over here, this new point, C prime. And by doing this, what we saw was that by taking this triangle, I could fold it again and again and reflect it again and again over various points and create the same triangle where these line segments were all going to be the same. And not only that, but our angle measurements continue to be the same along the axis of the origin point here. And we had the same triangle just going again and again, and we could do that again and again. So we said, reflect over ABC. We also had to rotate triangle ABC prime around A so that C prime matches up with B. So that was taking this point right here, and it said, well, we'll take this here and let's rotate ABC prime so that A around A so that C prime lines up with B. And when we do that, what we saw was that our angle measurements are identical. So even though we reflected it, it doesn't change anything in isosceles triangle. Our angle measurements end up being the same with that simple rotation there. So these angle measurements are all equal to one another in these bottom corners, just as the top ones are equal to the top measurements there. This is how an isosceles triangle works. When you look down below, we had a triangle like this, ABC, and instead of excuse me, draw a midpoint of side AC. Now midpoint means that it's going to be in the middle, and maybe you used a ruler to do that. You might have said, well, this looks like it's 5 7/10 or 5 6/10, something like that. And perhaps you used an inch ruler and you went, well, it's 2 1/4. So what would that be? That'd be 1 1/8. About here's the midpoint right there. If I rotated that around, the idea is that when I draw this shape, so I just copy it there, and you don't have to use a tracing paper, but it might help you a little bit if you're not seeing things right away. When I draw that shape, if I find a midpoint and I rotate it around that midpoint 180 degrees, when I snap that line in place, I end up with a parallelogram. And so I can put a point right out here where that's going to be. And if I used a ruler, I would have a line here and a line there because I rotated around that place. So when I rotate around a midpoint, or rotate a triangle side around a midpoint, I can create a parallelogram. And in doing that, I have two sets of parallel lines. I also have lines that are equal to each other. This length will be the same as that because I've simply rotated it, and that's the transformation. It's rigid, it keeps the same length. This length here would always be equal to this length there. Not a problem. The other interesting thing is because this becomes our B prime, our angle measurements also do not change. So this angle measurement here will continue to be the same as this angle measurement here. That does not change even though I'm making that rotation. Same for here. This becomes my A, but that rotation there, when I rotate it, it moved all the way over to here. That's going to be equal there. And our last one, that's going to be this acute angle here. This little skinny one for C down here, that whole thing ends popping up over here in this space there. So our angles remain the same, our lengths remain the same. Of course, I have to find the corresponding parts, and that's what we were looking at with that opening part of today's lesson. We then took a look at triangle plus 2 just to kind of prove that there, and we slid this triangle around triangle 1 in different ways by rotating it in different positions. So for example, if I took triangle 1, here it is here, triangle 1, and I sketched it out. If I rotated it around a midpoint of AC, if I rotate it here on AC, I find that it snaps in place and forms triangle 2. Right? So I could rotate around this midpoint right there to create a duplicate or a copy there. If I find a midpoint here, which that's a midpoint right there, and rotate this way, I can create triangle 3 by rotating it that way. So I can use some rotations around midpoint segments, midpoints of the line segments, to create some copies of the triangles as I move things around. But even by doing that, what's important to realize is that these measurements remain the same, right? So in my original, this length here, this AB, this is 2 diagonal, it lines up right there with that shape right there. That's the line segment. And they share that common edge, the same length, here to here. This same length, though, is the one that's over here, CD. That's where it's at. In the same way, this bottom line, BC, over here, BC, because the rotation ends up here being AD, there's my parallelogram, and it ends up being over here, AE, and it becomes that parallelogram. So I have a parallelogram going this way, right? And a parallelogram going that way, and those side lengths are the same. The other length that's the same as my original is AC, becomes this length right here, and that's the other one there. So I have a parallelogram here, parallelogram there. It all works out nicely. And as we said before, the angle measurements also correspond to one another. So if this is the point where the pink and the green come together here, I notice the pink and the green come together here, and the pink and the green come together here. They're going to have the same angle measurements there. You could do the same thing with the other ones to find out what your similar or your congruent angles are going to be and what they're going to line up and match at. Then you move down to the triangle plus 1 shape over here for 10.4, and we had again another isosceles triangle, which barely fits on my paper right there. And so if I trace this isosceles triangle, we had triangle ONE right here. And the first thing they asked us to do with triangle ONE was to reflect triangle ONE across segment ON. That meant that we were going to take this guy right here and we were going to reflect it across there to create this new triangle right there. So I have 2 triangles. I can go ahead and I can draw my dot to know where it's going to be at. Make a little point there, make a point there. Use my ruler or straight edge of some sort, and I can connect my dots to here and to here. And it said to label this point as point M. No problem. So what's the measure of angle MON right here, this angle measurement here? Well, this angle measurement, because we just reflected it across, it is the same exact angle, right? So there it is there, and there it is there. This continues to be 30 degrees from here. This one is 30 degrees. Now the entire length from here to here, right, if we added those up, would be 30 plus 30 for 60 degrees. So the measurement of MOE, right, angle MOE, the whole thing would be 60 degrees. So it's interesting to take a look at that. The other part we talked about was that this line remains 5. It stays 5. It stays 5 throughout the whole thing. This length here would continue to equal that length. And this pattern would continue. If you were to draw another triangle out to the side, over here, and make another point by reflecting over that line and making the point right there, wherever it needs to be. There's my little dot. Draw my lines here. Oops, got a little bump on my protractor there. And draw my lines. If I was to then say, well, what's this angle measurement going to be? Well, this should be 30 plus 30 plus another 30, which is 90. And I could take a look with a protractor and see right away that indeed, if I put my line there and my other line here, whoops, there we go, I have a point 0, 0, all the way up to 90 degrees. That becomes the length of the entire thing, 90 degrees. So it was just fun to kind of play with those and see how those measurements moved and changed as you went through today's lesson there, and looking at line segments and links and how those things stayed congruent. So in summary of the wrap up of the lesson today, your summary part, We learned that if we apply a sequence of rigid transformations to a figure, so a sequence of rigid transformation to a figure, then the corresponding sides have an equal length and corresponding angles have an equal measure. And so the picture they gave here for your summary is right here, where we take this shape right here, and we notice that this line, because we're reflecting it over, is going to have the same length as the other one. This angle measurement here matches that one there, as we said before. This line right here, because we're reflecting across here, is going to match that length right there. And then this B prime C would match B and C. And then, as we mentioned, these angle measurements are going to be the same. So this angle B is going to match B prime, just as this angle right here, C, would match over here. Blue and yellow come together, blue and yellow come together, pink and blue makes red, pink and blue make red. And so there's ways of looking at how that's going to work. I like to use lots of colors, just helps me visually see what's going on as I analyze the different shapes. Let's take a look at your homework then for tonight, because we have a couple flags which are made with lots of triangles. It says, describe the sequence of translations, rotations, reflections that takes the lower left triangle to the upper right triangle. So how do we take this and get it over to there? How do we take it and move it over there? This shape here has to be spun, doesn't it? It has to be rotated. We could begin by translating it if we wanted to. We could think about doing a translation to the right to get it over here. And once we get translated right over here, it would be something like there, all the way over here, running off the paper. And we've learned that if we find a midpoint and we do a rotation, we should be able to rotate it, in this case, clockwise or counterclockwise, 90 degrees, in order to get that to snap into shape, into place. Let's take a look and see if we can do that for real. So if I take this line, this triangle, and I trace it out, I have something that looks like this and this. If I translate this point over here to this point right there, so sliding it to the right, and then I find a midpoint about here and rotate 90 degrees, I can get that to snap in place right on top of that other triangle. So the key is to translate to the right, to the other point, and then to find a midpoint in this segment to then rotate it there. For number 2, we have an older picture of the flag of Great Britain. There's a rigid transformation that takes triangle 1 to 2, another takes 1 to 3, another takes 1 to 4. What we're saying is because it's a rigid transformation, these triangles are all going to be equal to one another. It says to measure the lengths of triangles 1 and 2. What do you notice? Well, for number 1, we on my little centimeter ruler here, we're about 1.2 in our height, 1.2. And over here we are about, what do you know, 1.2, exactly the same. If I looked at my length of the triangle, I might notice that I have 2.5 as a length there. And over here on this length, starting at the tip, I also have 2.5. So when measurements here, I see that my triangles are the same from one to the next. What are the side lengths of triangle 3? I'm going to say they're exactly the same. And you need to measure it to verify. But I'm going to say the same because with a rigid transformation, everything stays, what's the word? Congruent. That means they stay the same. Angles stay the same and side lengths stay the same. This is going to match this, which is going to match this, which is going to match this. That's the important thing we learn with those rigid transformations. It has to, all 8 triangles in the flag have the same area? Well, take a look at these. Do these triangles look exactly the same? I'm not really sure there. If you're not positive, do this. Take one of the small ones, trace it, maybe even shade it in a little bit if you want to see it better. Shade it in, and then put it on top. Well, if I put that triangle on top of there, well, gosh, it's a little bit too small, isn't it? There's this whole extra piece here that's not even included. So we would say, nope, they do not have the same angle. This area is larger than that area, not right there. Looking at number 3. Number 3, which of the lines in the picture is parallel to L? So the one we're trying to evaluate here is we have this one right there, and we want to know which one of the lines is parallel. Parallel means that they're never going to cross, they're never going to meet, they're going to go on and on forever and ever. My problem here is with P is that obviously it crosses. So we would say it's not P. With M, because the distance gets closer the further we go, at some point they're going to match and meet and they're not parallel. So the one that's parallel we would say is K. And we say it's K because they are the same distance from one another and they would never meet. You could kind of check that if you wanted to, just for fun, by using a ruler and say, well, over here, we're about 1.6 is the distance from there to there. And over here, we are still at 1.6. So my distance stays about the same from 1 to the x. 1.6 centimeters, 1.6 centimeters. You're not expected to measure those to verify. You're just supposed to kind of eyeball it and see for right now. B, explain how to translate, rotate, or reflect line L to get K. So how would I get this one to that one? Well, I'm probably just going to translate it up, right? I could translate the whole thing up that way to make it line up there. I could also probably find a point of reflection to make that work and reflect it over something there. And I could maybe find a midpoint that I could spin the whole thing around. Could work too. Couple different ways to get that one there. Now how to get line P, how to translate, rotate, reflect L to obtain P, this would be a rotation, wouldn't it? To get this line right there, I'm going to have to take that one and do a rotation. There's no other way around that one, right? I'm going to take this line shape here, and to make P, I have to do a rotation. I'm not sure what the angle measurement would be there. I could measure it if we wanted to check and see what that could be, just for fun. Just for fun? Well, that's fun, oh boy. Right? So I find out where they cross at, and I look and say 0 goes to there, about 80 degrees. It's about an 80-degree rotation to get that one to take place. Again, not important there, but just a way how you would do that. Okay? Finally, number 4, it says point A has coordinates 3, 4. After a translation 4 to the left, reflection across the x-axis, translation 2 down, what are the coordinates of the image? All right, so it looks something like this. I'm going to draw a little grid right here. We're starting at 1, 2, 3, 1, 2, 3, 4. We're starting about here at 3, 4 with our shape. We're going to go 4 units left, which means my x value needs to move 4 spaces this way. So to go 4 to the left, I'm going to go from 3 to 1, 2, 3, 4 to -1. I'm just going to put a dot there to say that's step 1. So I got over here at -1, 4. That's my translation left. I'm not done yet though. Now to reflect that across the x-axis means that my x value will stay the same, but my y value is going to become negative. So I'm going to go 1, 2, 3, 4. I'll be at -1, -4 because I reflected across the x-axis. I went this way across the x-axis. Then it says translate this 2 units down. So 5, 6, and -6 is now where I go. So I'm at -1, -6 is my final home for this coordinate. -1, -6. So it takes some time to make that happen there, but it took 3 different transformations to move this point all the way over here, sorry, right here, and that's our final point there. All right, so there's my answers here, but I started up here and did 1, 2, 3 moves to get it down there. Our last one for the day, we have triangle XYZ, and it wants us to do several rotations of XYZ to make a nice shape. So here we go, we have XYZ, I'm going to draw it right here, XYZ, I trace that right there. And the first thing it wants us to do is rotate it XYZ 90 degrees clockwise around Z. Alright, so clockwise 90 degrees. I'm going to draw a little hashtag here, make a T, so that when I snap this in place, I wait till I line up my T and I snap it in place and I'm something like that. Alright, so 90 degrees clockwise is going to be here, something like this. Again, put my points down. Maybe I poke a hole through the paper to get my point just right. Put a hole there and poke a hole there. Whoop. And put my line there. And then I can draw my lines and my line and my line there. And then it says to do 180 degrees around Z. So I'll put it back where I started at. 180 is going to be, snap that thing in place, 90 to 180. So we're about here, right? Something like this. So I put my dot down, and draw my line. This should be a straight line there, should be. Got a line there and a line here. And I'm going to go 270, which means I'm just going to continue the rotation around one more time until I get where I need to be. And I have a dot here and a dot here. Again, this line is just going to continue. All right, we're going to continue this along to make a straight line there. So there's my 90s, right, along this line here. And then my other one, oops, where'd it go? Right there, is that it? Yeah, that's it. Got that one, and we have that one right there. So about something like that when I make those rotations as they come around and come together. And you could check that on your own, but it should look something like that as you rotate that around and make your nice shape. Okay, hope that it helps you out a little bit there, and good luck for the other stuff.